In chapter 2 set theory, I already discussed sets, set operations, functions, sequences and summations, cardinality of sets, relation and their properties, NR relations and their applications, reprinting relations, closure of relations, equivalence relation and partial ordering. These all topic I already finished. Next I will discuss groups. That's the last topic of set theory. Before groups, I will discuss some basics of group theory. First is algebraic structure. A non-empty set S is called an algebraic structure with respect to binary operation. This can be anything. It can be plus, minus, any binary operation. So if A binary operation B belongs to S, for all A, B belongs to S, then this star is a closure operation on S. N stands for natural number starting from 1 till infinite. Z for set of all integers, positive, 0, negatives. Q set of all rational number. R set of all real number. C set of all complex number. I already discussed all this, but now I will use it, so that's why I am revising all this symbol. Let's see some examples of algebraic structure. So n plus is an algebraic structure. If you do addition of two integer, it will be another positive integer that comes under n. So it is closure. N multiplication is also an algebraic structure, as multiplication is a closure operation on integer. But n minus is not algebraic structure with respect to minus. Let's take an example. 3, 5. Both are positive integer. Now 3 minus 5, it's minus 2. Minus 2 doesn't come under n. N contain all the positive numbers, as minus 2 not comes under n, hence it is not closure. So minus operation is not closure on n. Next, n division is not an algebraic structure, as by division we may get real number. It's not guaranteed that it will always come under n. So it is not closure. Then for Z, plus operation, multiplication operation and minus operation are closure, as Z includes negative number also. So 3 minus 5 minus 2 comes under Z. So Z is closed under plus, multiplication and minus. Next, Z division is not an algebraic structure, as by division we may get real numbers. Next is semigroup. An algebraic structure is called semigroup if it supports associative. Associative means A star B star C equals to A star B star C. This star can be any binary operation. If it is closure and associative, then it's semigroup. Let's see some examples of semigroup. N plus is a semigroup, as plus is associative. We already know plus is closure, plus is associative, hence addition is semigroup. Then n multiplication is semigroup, as multiplication is closure, also associative. Now n minus is not semigroup, as minus is not closure and not associative. For semigroup, it should be algebraic structure. So first we'll check for closure, then associative property. N division is not semigroup, as division is neither associative nor closure operation. Next is monoid. A semigroup is called monoid if identity element exists. So there should be unique identity element. If a unique identity element exists, then it's a monoid. What is identity element? In case of addition, we can say 0 is the identity element. Any number addition 0 will be same number. In case of multiplication, 1 is the identity number. Any number multiplied by 1 will get the same number. So A star E equals to A for all A belongs to S. Then E is the identity with respect to star. This star can be any binary operation. It can be addition, subtraction, multiplication, anything. So for monoid, it should be closure, associative and identity. Now example 3, n multiplication is monoid, as 1 is the identity element and that comes under n. So n multiplication is monoid, as it is closure, associative and identity element exist. N plus is not a monoid, as A plus 0 equals to A and 0 doesn't belongs to n. In some book you will see n consider 0, 1, then all the positive integer. In some book you will see n start from 1. So it varies from book to book. Here we are considering n contain all the positive integer without 0. As 0 doesn't belongs to n, hence plus is not a monoid. Next, z plus is a monoid as 0 belongs to z, and 0 is the identity element with respect to addition. Z minus is not a monoid as minus is not associative, hence not semigroup and not monoid. So for monoid, it should be closure, associative and identity element should be exist. Next is group. A monoid is called group if for each A belongs to S there exists an element B belongs to S such that A star B equals to B star A equals to E. We can say B is the inverse of A. So one monoid is called group if inverse exists for each element. Let's see some examples. Z plus is a group as A plus minus A equals to 0. So here minus A is the inverse. Now n multiplication is not a group, as in case of multiplication, A multiplication 1 by A will be 1, but this 1 by A doesn't belongs to n, hence it is not a group. So for group we'll check closure, associative, identity and inverse. If it is satisfy all four, then it's a group. Identity element is unique, but for every element there can be different inverse. Next is Abelian group. A group is said to be Abelian if it supports the commutative property. Means A star B equals to B star A for all A B belongs to S. Now an example, Z plus is an Abelian group. Here plus is closure, associative, it have the identity, it have the inverse, also it satisfies the commutative. Hence it is a Abelian group. So let's gather all these. If it is closure, then algebraic structure. If it is closure plus associative, then it's a semigroup. If it is closure, associative and identity element exists, then it's a monoid. If it is closure, associative, identity and inverse, then it's a group. If it is closure, associative, identity, inverse and commutative, then it's a Abelian group. Now one example, set of all non-singular matrix of order 2 cross 2 is a group with respect to matrix multiplication but not an Abelian group as matrix multiplication is not commutative. So this 2 cross 2 matrix multiplication is a group but not Abelian group. In today's lecture I discussed what is algebraic structure, what is semigroup, monoid, groups and Abelian group with examples. In next lecture I will discuss some more examples. If today's lecture is helpful for you, please like, share and subscribe. Thank you.